So good afternoon, ladies and gentlemen, dear colleagues. This is the first webinar of the joint webinars of the Belgian Physical Society and the International Solvay Institute. This is a set of 5 talks on fusion. The aim of the talks is to make fusion much more publicly accessible, understandable for anybody who is interested, students, teachers, members of the public, no problem. Please feel free, everybody who is now already present, to distribute the news to other people interested. There's no problem, it's fully free. And as I said, the aim is to make fusion as accessible, also to show you the latest status of the research in this field by selected didactic experts, each in their own domain. And this afternoon, we start with the presentation by Dr. Julien Hillairet, who is a maître de recherche at the Institut for Nuclear Fusion Research in the CA in Cadarache in France. And he will give a general introduction to fusion research, to remind you the basic principles, to tell you where we are in different fields, and to also explain you how it looks for an extrapolation to a future device that could provide energy to the grid. And so, Julien, I would ask you to start your presentation. The floor is yours.
Thank you, Dr. Langena. So it's my pleasure to be here today to introduce you about the nuclear fusion research, a very exciting field of research, but also you will see a quite complex field. So what is the outline of this talk? So first I will make a minimal energy outlook to know where we are, and then I will speak about the basics of nuclear fusion, the physics and the engineering of magnetic fusion in particular, and the magnetic fusion in Europe, in the world, and the future and the prospect of fusion for the future years to come. So first, I will start with a kind of small energy look. So you will see that I will probably push some open doors, but anyway, it's important to know and to understand what is the context of this research. So as you probably already know that where does all energy come from? So currently in the world, if we average slightly more than 1/3, so 36% of the global electricity comes from low carbon source, that is from nuclear, hydropower, wind, solar, and other kind of renewable. That means the rest, so more than 60%, still come from coal, gas, and oil. But electricity is only 1/3 of the problem. The rest, if we take the global energy problem, the total energy, which includes transport, heating, and electricity, you will see that the picture is very different because most of the energy, more than 80% of the energy in the world is produced with fossil, with high carbon sources, oil, coal, and gas. The current situation is now quite well known, at least scientifically speaking. It has now been proved that the human influence has warmed the climate at a rate which is never seen before, at least in the last 2,000 years, and if not in the last 100,000 of years. And 2 years ago, the atmospheric CO2 concentration has never been so high, and it's still same in 2021 in comparison to the last 2 million years. Which what also has been demonstrated is that the global surface temperature increased faster since 1970 than in any other 50-year period over the last 2,000 years. So this is something which you can see on these plots, which is come from the latest IPCC assessment reports, the physical science basis that has been released a few months ago, that shows how the change in the global surface temperature in the last years, and the last 10 of years, and even up to the 100,000 of years. The main problem is that the future emission will also cause future additional warming. So in fact, it's a twin problem of global energy, because currently those that do have low carbon emission, they lack access to energy, which is what you can see on this plot. This plot is showing the annual consumption, the average CO2 emitted by capita versus the GDP per capita. And you see that the average is around 4.8 tons per year, and there is a lot of countries which are below this average, and that only one thing is to go above this average in order to live more easily. So currently, a large share of those people in countries with a low GDP do not have access to electricity at all, or in a very scarce situations. And the second problem is that the people that have access to energy, they produce a lot of greenhouse gas emission, and too much. I remind you that the goal is to have in less than 50 years, have a net emission objective to be close to zero. And you can see that all of these countries, like France, like Belgium, we are way, way, way too high with this respect. So what we need, what we lack currently is a large scale energy alternative to fossil fuel that would be cheap, safe, sustainable, and also which we could control, because when you want about the electricity, you need to produce electricity when people use it, because it's complicated to put the electricity somewhere. So tentative of summary, it's that currently the energy is massively dependent on greenhouse gases producing technique, and the gross domestic product is tied very tightly to the energy consumptions. So how can we solve the equation? First, one, to decrease the consumption of fossil fuel, and two, to maintain the energy consumption level in order to maintain correct and satisfactory lifestyles. So one of the solutions is to go into more electrifications, and of course, electrification without the use of fossil fuel like coal or gas. So there is few options for that. Hydroelectricity, of course, but currently in Europe, maybe we are close to the maximum of the hydroelectricity potential power. Photovoltaic and thermal solar and wind, they are cheap techniques, but the problem is the intermittency and the storage. We cannot store electricity much. And also, we need some mineral resources in order to build those photovoltaic panel, and also to build the coil inside the wind tower. There is a fission technology which already works in many places in the world, but currently the risk versus benefit always lead to discussion, at least in the public acceptation way. So the question that I will address in this talk, could fusion also be part of this solution? So this is what we will discuss just after. But first, before discussing about the solution, let's see what is the nuclear fusion. So this is close-up of the sun, a real picture that has been taken, and just to remind how small we are, this is approximately the size of the Earth. So atoms, every atoms are made of protons, of neutrons, and of electrons. So what we define the binding energy is the energy which is released when a nucleus is created from protons and neutrons. So when you want to create something, you need certain binding energy in order to achieve this something. The greater the binding energy per nucleon, the greater the atom stability. That means at some point, there is some atom that are at the top level that cannot be destroyed, like iron or nickel. They are the most stable atom. And this graph is showing this binding energy per nucleon versus the atomic mass numbers, that is the sum of the number of protons and the sum of number of neutrons in the atom. There is two possibilities to create new elements. Either you take a light element like hydrogen, so the proton, or isotope of hydrogen, or a little bit heavier element, and you fuse them together. You stitch them together in order to create a more heavier element, or an element which has more proton and more neutrons. So this is the fusion, and this creates a lot of energy. There is a second process, which is fission, which is the opposite. In this case, you start from a heavy element, and when you split this heavy element into more lighter ones, you also generate a lot of energy. So here we will discuss about the fusion, because the fission is the technology which is already used in what we call the nuclear central plant. So this is something that we know how to use it to generate electricity. What we don't know yet is how to use fusion to generate electricity. A reminder is maybe that all the stars, like our sun, are all powered by fusion. So they are in the sun's core. It's also a real picture. The protons fuse to create helium. So in fact, the sun is a big machine to transform the hydrogen into helium via a cascade of complex fusion reaction and different nuclear reaction that you can see here. Most all of these nuclear fusion reaction happen into the core of the sun, which is the hottest place in the sun, which is about 15 million degrees. And you see that the temperature decreases as we go out of the sun. But by the way, do you know what is the sun core power density? So the theoretical models say that the sun's interior indicate a maximum power density of about less than 300 watts per meter cube. So let's suppose that magically I go into the sun, I take 1 meter cube of the core of the sun, and I put this 1 meter cube of the core sun inside your house. Will it be sufficient for you to eat this winter? So with what can it be compared? Is it the same power that an exploding hydrogen bomb, 1.5 ton of TNT, a certain number of swimming otters in terms of power density, or a compost pile? Well, maybe you will be surprised to know that, in fact, the sun is very, very inefficient. In fact, 1 meter cube of the sun generate less energy than your own body, for instance. So it's generate similar energy than a compost pile. So can we use fusion reaction to produce electricity at some point? Alors, currently, almost all the electrical power is generated with turbine. So that this turbine, the energy that make this turbine works come from wind, from water, from steam, or from hot gases. For example, for coal and for nuclear fission reactor, they basically are machines to boil water, and we use this very hot water to drive steam turbine. Well, but in fact, for fusion, we exactly want to do the same thing. We want to have somewhere control fusion reaction that could boil the water and drive steam turbine. So the problem, as we just seen, is that the sun fusion process are very, very inefficient. Alors, this picture is showing the fusion reactivity, which is similar to the probability of element to fuse versus the temperature of this element. And you see that the probability of the fusion of the proton in the core of the sun is about here. So it's very, very low probability. It's statistically, it's very, very low in terms of occurrence, but it is compensated by the huge volume of the sun. So we cannot take exactly the same fusion reaction in a reactor, because I mean the space is not as big as the sun. So we need to find something else. And fortunately for us, there are more efficient fusion reaction. And the easiest one that we could achieve is the fusion reaction between deuterium and tritium, DT. So this is the blue curve here. And you can see that the probability of achievement of this fusion reaction is way much more probable than for the one which is in the sun. So the fusion reaction, the DT fusion reaction, can be written like that. So deuterium plus tritium, this fusion reaction will lead to an helium ions plus a neutron. What does that mean? So what are those deuterium and tritium? So both of them are hydrogen isotope. The deuterium is a stable and a relatively abundant isotope of the hydrogen because it's naturally occurring in the Earth's water. So less than 0.02% seems very low, but there is a lot of water on Earth. And if you put those numbers in terms of how many years you could use a fusion reactor, you will achieve a huge number of years. The second ingredient is the tritium. Alors, the tritium is different because the tritium is a radioactive atom, which is unstable with a half-life of around 12 years. That means if you have 1 kilo of tritium, 12 years later, you will have half of 1 kilo, etc., etc. So it's very rare because this half-life is quite low to the scale of the Earth. There is almost no tritium on Earth except the one which has been produced in certain kind of nuclear fission reactor. So if one wants to use this reaction in a future fusion reactor, you need to find a way to produce this tritium. This fusion reaction will produce two things: an helium particle, so it's stable, so it's it's not radioactive at all. You can fill bottle with this helium and you can sell it if you want. And this fusion reaction will also produce a neutron with a high energy, 14 MeV energy. Both the helium and the neutron will produce a lot of energy, 17 MeV. Alors, the idea is to use these neutrons and to produce in situ inside the future reactor the tritium in order to be in a closed loop. The goal is to, if you impact some lithium-6 in particular, with a neutron, you will produce tritium and also helium. And the idea is to use this tritium, hence produced, and to re-inject into the loop, and then you will be in a closed loop condition. You will not need tritium from external sources. Alors, to say a word about this energy, 17 MeV, that's maybe not something that talk to most of you. So it's a lot of energy, but okay, compared to what? Again, the objective is to use a nuclear fusion reaction to produce energy, produce heat to boil the water and to use to make electricity. The real motivation behind that is, okay, let's suppose you will have a house and you will have to heat your house and consume some electricity on your way. So typical house requires something like 10,000 kilowatt. So it's during 1 year. This is the energy which is needed for your house. So how much wood would you need in order to produce this energy? So assuming, of course, a perfect conversion. So if you do the calculation, you will need more than 2 tons of wood, more than 1 ton of coal, something close to 800 liters of oil, and almost the same for gasoline, which is super oils. If one would like to use uranium to power his house, he would need only a little amount, 86 grams. And the main point with fusion is that you will only need 1.8 liter of seawater. And here you see what is the real motivation between fusion, because since there is a lot of seawater, there is potentially a lot of energy here. But we need to achieve and to control this fusion reaction, so DT fusion reaction. And there is a condition for that. The condition can be expressed as the product of 3 quantities, what we call the triple product. So those 3 quantities are the number of ions per unit of volume, the temperature of the ions, and the energy confinement time, which is the rate, the time by which the energy leaks of your plasma. And the product of those 3 quantities must be higher than this value. Okay. So as we see, we cannot use the same fusion reaction like in the sun, except of course in the movies. On Earth, that is not possible. So in order to achieve fusion with deuterium and tritium, we need to have a density of ion of in order to 10 to the power 20. It seems a lot, a high number, but in fact, it's the atmospheric density, so the air that you can breathe, divided by 1 million. So it's a very tenuous gas. We need to achieve the high temperature, 10 times the sun core temperature. That means at least 150 million degrees. And we need to confine correctly this energy for a time which is sufficiently long in order for the fusion reaction probability to occur. And this is the energy confinement time, which is on the order of seconds. In addition, if you want to make a continuous production because you want electricity 7 days a week and many months per year, you want to produce this energy during a longer time, and you want also to have a closed loop of the tritium production in order to not create too much tritium and also to not need tritium from other kind of system. So what are the consequences of these three numbers? Because the atmospheric density is divided by 1 million, that means it's a very tenuous gas at a high temperatures, and it's very tenuous. The advantage is that the total fuel which will be contained inside your reactor will be very, very low, in the order of 1 gram or less than 1 gram, a few hundred of milligram. That means at a time, let's suppose you open your reactor of fusion reactor, there is less than a gram of deuterium tritium fuel, so very, very little. At the temperature of 150 million degrees, the gas is deuterium and tritium is in the plasma state, and we will see just after what it means. And the second quantity, the energy confinement time, means that we must minimize the energy losses. That means the energy that leaks out of our plasma. We should do the best that we can. So what is a plasma? The plasma is commonly stated as the fourth state of matter. So the plasma is a gas of ion and a free electron. So there is ion and the electron. They are not attached. They are not bound together. They are free. And this happens only when you heat some gas to high temperature. So at least a few million degrees, you are a fully ionized gas. It's in fact the most abundant form of matter in the universe. And if you look outside of our little planet, you will see that in the interstellar medium, in the solar corona, this is all plasma. The flame that we can see, more often is also a kind of plasma, lighting as well. And these charts show the different kind of plasma that depend of the plasma density, that is the number of ion in per meter cube versus the temperature of this ion. And you can see there is many scale, very different order of magnitude of difference. That means there is many different of plasma. The one that we are interested the most for fusion is the one with, let's say, average plasma density, but very high temperature. So what are the pros and cons of fusion if we make a list? So the pros is that does not use fossil resources. You don't have to mine. Of course, you need to build your reactor and to transport the component to build your reactor. But the fusion itself does not produce greenhouse gas. It only produces helium. That again, you can fill bottle and sell after refuel. There is plenty of resource, at least in theory, and for more than thousands of years. You can build large production unit, typically the same amount of production unit like for coal or for fission reactor. You can also control this power production. That means you can generate electricity when you need it, which is important in comparison, for example, of solar and wind nuclear source. There is little nuclear waste and also nuclear hazard, which are less harmful than for fission reactor. Again, and also it's also difficult to turn secretly into a military facility. But there is also cons. Still, there is some nuclear hazard. You need to handle correctly this tritium, which is radioactive. And the fusion reaction will produce neutron with a high energy, and this neutron will impact the reactor which is around your plasma. That will impact the material and the life of those materials. You need a highly sophisticated technology in order to achieve the plasma of 150 million degrees inside a machine. It's not an easy task. And of course, it will not be ready before 50 to 100 years. So just to say it, it's too late for climate change. That would be, of course, very useful in 50 to 100 years. But right now, you cannot rely on fusion to change things. But the main point is it has to be demonstrated, because so far there is no fusion reactor. It's only a sketch. There is only some experiment around the world. We will talk about that. But nowhere we have demonstrated that we can reliably generate energy with fusion. But anyway, the fusion research is necessary on the long term, because fusion is the only carbon-free, fossil-free, intensive and controlled technique that will remain available in, let's say, 100 years and even after. So if we want to have this possibility in the future, we need to do research now. Now, there is different way to control the nuclear fusion, and different way are investigated. Again, these different way are a different way to play with this triple product, triple quantity. There is the inertial fusion, which goal is basically to maximize the density of ions and the temperature. So one way to do that could be to fire the deuterium-tritium mix with a powerful laser in order to make this little ball here field of deuterium and tritium to be implode and to create energy with the fusion. That's the principle of the inertial fusion with laser. There is few experiments in the world that do that, the laser megajoule in France and the NIF in the USA. And there is another technique, which is the magnetic fusion, which, at the contrary, try to maximize the temperature and the confinement time. There is different technique that we will see to do that. Most of this talk now, I will talk about magnetic fusion. Just some promotion for the future of your webinar. You will have dedicated talk to those different solutions, to the inertial fusion, to what we will see the stellarator solution, and to ITER, which is the tokamak solution. So now let's talk about the physics and the engineering of magnetic fusion. So in a non-magnetized plasma, it's like a bit of Marseille in the morning. You have car here and there is no clear way how to the electron and the ion go in every direction. There is no preferred direction. This is a plasma which is not magnetized. If you superpose a magnetic field into this plasma, then the particle will follow the field line of the magnetic field. In fact, they will gyrate about the magnetic field line. So then you will transform your mass, let's say, into a sort of highway for ions and for electrons. They are confined by the magnetic field, and this magnetic field is, let's say, forcing the direction of the ions and the electrons. So that's a good way to control a plasma. But in this case, the confinement is perpendicular to the magnetic line. That means the ion and the electron, in theory, will not change line from the field line they are following. And moreover, these ions and electrons, they go very fast on the line they follow, about few hundred of kilometers per second. So if you need to build a device that will confine such a plasma, you will need to build a device which would be very, very long in order for the fusion reaction to occur. So few thousand of kilometers, that's not very convenient. So the idea, okay, let's do a roundabout. Let's close the field lines. Let's create a magnetic field line, which is the same like a roundabout. So let's make a magnetic field line going around. If you do how to do that, the way to do that is to coils all around, like the quarter of an orange. And if you do that, you have some geometry which is like that. So you have different coil, and those different coil, when there is current that flows into this coil, they will create this magnetic field. Well, perfect. We just make a magnetic bottle. Well, in fact, it's not that easy, because if you just do that, in fact, if you look closely, you will see that the magnetic field which is inside your device is higher than the magnetic field which is outside your device. So there is a gradient of magnetic field, and both the curvature and this gradient will generate vertical drift that are in opposite direction for the ion and the electron. The electron will go at the top, for instance, and the ion will go at the down. So your plasma will be separated, the ion and the electron will be separated. And if you separate the electrical charge, what you will create is an electric field. And if you create an electric field in a magnetic field, then you create a new force, which is a new drift that will push your plasma outward to the wall. And then, end of the story, your plasma is unstable and it cannot be sustained. So the solution, there is two solutions, at least two solutions for that. One solution that has been invented in the 50s by the Soviet physicists Igor Tamm and Andrei Sakharov, which is the tokamak, which is the Russian translation for toroidal chamber with magnetic coil. The principle is the following. In order to avoid this charge separation and the fact that the plasma goes into the wall, the idea is to add a new magnetic field that we call a poloidal magnetic field that will be induced by a current that is flowing in a plasma. The plasma is a very conductive material, so you can induce a current inside this plasma, and this current will generate a magnetic field which is in the opposite direction than the field generated by your coil. And if you do the sum, then you have helical magnetic field, and it's a kind of washing machine for particle, for ion and electron. The ion and the electron, they will turn around your machine, but in this direction, but also in the vertical direction. So the ion and the electron will be always mixed, and then your plasma is stable. The other advantage is, like in a bread toaster, if you use a current inside the wire, it will hit. It's exactly the same in the plasma. The current that flows into the plasma will hit the plasma at least to a certain temperature, typically one of few million of degrees. The other possibility is to avoid the charge separation is to add a poloidal magnetic field, which is directly created by specific coil around the vacuum vessel. That means coil that generate these LECT magnetic field lines. So there is different technique to do that, and few experiments that already exist, like the large helical device in Japan or Wendelstein 7X, for which you will have a specific talk soon. Alors, the stellarator research line remain in terms of performance a little bit behind of the tokamak because it's much more complicated to manufacture. You will see that this is a real machine that has successfully been built in Germany. It's not just a crazy image for a scientific. It has really been built and it works quite well, but it's more complicated to build, and for this reason, there is less stellarator in the world. But there is also advantage with stellarator that you don't have to have this plasma current, which generate a lot of instability in tokamaks. The fusion reactor, at least the fusion experiments, have progressed since the beginning and since the 60s. So we have plotted here the performance in terms of the triple product, or the density times the temperature times the confinement time versus the temperature. So this is the first experiment in Russia, T3, that show to the world that tokamak could be an efficient way. And you see that from this very early time, the progress has still been continuous, and we have gained performance by a factor of 1 million between the 60s and with the experiment that we are using now. You can see some name of the different experiments that exist in the world. And in fact, we are never been so close to a reactor for which the fusion power would be larger than the power we have injected into the plasma to achieve fusion, which is what we call the Q factor. That is the ratio between the power that goes out for the plasma over the power that goes in the plasma to achieve fusion. So far, we never achieved something larger than 1. And the target for the next big experiment, which is ITER, is to achieve Q equal 10. How did those evolve? So in fact, there is 2 branches of research for fusion experiment. Let's say there is two branches. So you can target to have long plasma duration. That was in particular the specialty of the tokamak Torsupra, which has been built in France in 1988. It's used superconducting coil and actively cool the plasma facing component. And with the use of that, you can make long duration plasma. So this video is showing a plasma into Torsupra, which is 6 minutes and 30 seconds. And we will not watch the whole video because it's a bit boring. But those experiments are made with a little fusion power or equivalent of fusion power. And what we are interested in is also to demonstrate that we can create a lot of power. And another machine, a European machine, which is JET, which is located in UK, has start operation in 1983. It's currently the biggest tokamak in the world. And this is a machine with which the world record in the fusion energy produced has been made in 1997. 16 megawatt of fusion power has been produced inside the plasma, but we needed more power to achieve to hit the plasma at this time. And if you make the ratio, you are below than 1. It was 0.66 around. And still, that means you need more power to hit the plasma than the power you get from the plasma. So ITER, the next big experiment, is the integration of both the tokamak that have worked for long plasma duration technologies and the tokamak that have worked for high performance plasma. This is the integration of all of this technology, but also the result of the know-how acquired in many other machines around the world, in Europe and in the world. ITER is just an experiment. It will not generate any electricity. It's only an experiment to demonstrate that it is maybe feasible to produce more power than you needed to achieve fusion reaction. And there will be a step. If ITER is a success, of course, there will be a step after, which will be an actual demonstrator that could demonstrate electricity generations. So it's now time to speak about the magnetic fusion in Europe and in the world. So there is, since the 1988, the second United Nations Conference on peaceful use of nuclear energy, all the fusion research has been declassified. That means from those days, there is a big collaboration between different countries, many countries in the world about fusion energy production, at least for peaceful production, for electricity production. So you can see here a picture of the various different position of fusion laboratory, as well the one that's directly linked to ITER. ITER, as I said, is the next step. It's an international collaboration which has been organized with 7 partners: the UA as plus Switzerland as a partner, China, India, Japan, the Russian Federation, the Korea, and the USA. The objective of ITER is to demonstrate the scientific and the engineering feasibility of a fusion for energetic pulse power, but only to demonstrate, not to produce electricity again. ITER will use mixture of deuterium and tritium plasma, and we expect that in ITER, the fusion heating power, that means the fusion which is generated inside the plasma by the production of helium, which is also called alpha particle, will be higher than the other heating method. So first, what we want to do with ITER is to produce that the Q ratio is higher than 1. That means we produce more energy than we put into the plasma. But we want to achieve Q equal 10, a situation during which we don't need anymore heating the plasma because the fusion power that will be produced inside the plasma will be sufficient to heat the plasma by itself. Just to say a word about the order of magnitude and the size of ITER, you can see here a sketch comparison of the cross section of the different machines. So all the three here are machines that existing, so Torsupra, JET, and GT60SA, which is a recent machine built in Japan, and ITER. And you can see that ITER is much more big. Now there is a reason why it is so big machine. It's because technologically, we are kind of in a stuck situation because, as I say to you, you need to maximize three quantities: the ion density, the temperature, and the confinement time. We cannot, with magnetic confinement, we cannot increase the density too much because then we trigger instabilities. We cannot increase the temperature much higher than what we already know. Not a factor 10. So the only, let's say, only button that we can play with is the confinement time. That is, let's say, the time by which the energy is confined when you stop heating the plasma. How much time the energy is leaking from your plasma. And this quantity is directly linked to the volume of the plasma. So if you have a bigger machine, you have a bigger volume of the plasma, then you have a bigger confinement time, and then you have bigger performances. And when we say that there is a big machine, you can see here a sketch of a human versus the ITER machine. So it's like a big cathedral. And I will, if you can pass by the south of France in Cadarache, where ITER is built, you can visit for free ITER, which is currently under building, and I really recommend you. So there will be a talk dedicated to ITER by Dr. Alberto Duarte. ITER and after, there is a lot of challenge to be addressed by ITER and by future experiment, and this is a non-exhaustive list. ITER will be the first machine in which we will have, let's say, burning plasma. That is plasma in which the fusion heating power will be dominant versus the other heating system that heats the plasma. It will be also an important for demonstrate the remote handling techniques, because during and after operation of a deuterium tritium plasma, you cannot enter into the machine anymore because they will be radioactive and a human cannot enter. So all in-vessel component will only be handled remotely using robotic systems. So it's not an easy task. ITER will be also a demonstrator of the different concept for creating tritium using lithium. The lithium, when impacted by a high energy neutron, can generate tritium. But this needs to be demonstrated, at least the technology for that needs to be demonstrated. And a future reactor should be fully autonomous for itself, but also in order to produce enough tritium to start the next reactor. ITER will also be a test bed to study the short and the long-term material issue, because we need in a fusion reactor high heat flux plasma facing component, and there is many physics behind, like erosion, deposition, dust. We also need to study how the material will evaluate with respect to the high energy neutron irradiations. And also something that there is not so much research on is how to produce steady state plasma, because we need to produce plasma for minutes, But I mean, what we want at some day is to produce plasma for hours, for days, or for months. And that, so far, we don't know how to do it. So to summarize, let's make an analogy between a barbecue and a fusion reactor. You will see there is something in common. In a barbecue, you need a match to initiate, to start up the barbecue. Once the coal is burning, you need the temperature, the combustion of the coal will be used for the self-heating, and then you will get energy. And unfortunately, you will also get CO2 as well. And at some point, you need to put back some coal in your barbecue because otherwise it will stop. In a fusion reactor, it's a bit of similar. You need some additional heating in order to achieve the fusion reaction, so the correct temperature, in order to achieve fusion reaction. And there will be part of the energy will be used to heat the plasma itself, ideally 100%. And from that, you will get some energy and some neutrons, and both of them will be used to heat the water and at the end to make steam turbine. And at the same time, you need to refuel in permanence your device. You need to put new deuterium and new tritium, otherwise the fusion reaction will stop because you will produce helium, but at some time you will have only helium and then that will not work anymore. So you need to fuel as well. And in the same time, from the neutron, you need to produce new tritium in order to fuel your plasma. So as a summary, the fusion is the energy which has many attractive features. So it's carbon-free, safe, controllable, it's a controllable source, plenty of resources from seawater in particular, but there is also a large number of plasma physics and engineering issues to address. So ITER is the next step, is the next magnetic fusion experiment that is an international project that will address many of these physics and engineering issues, but not all of them. So there is still need some research in parallel of ITER or after ITER. The goal of ITER is to demonstrate the feasibility of the fusion in order to produce energy. And to be clear and very honest, fusion is not the today answer to climate change. However, even if the route ahead of us is quite long, it's worth searching for this large energy alternative to fossil fuel that could be cheap, safe, and sustainable. And maybe even if it's in 50 years or 100 years, probably we will be very happy at that time to have this technology available. I would like to thank you for your attention. I've put here some references that are also very clear and very accessible for even for non-physicists and non-scientific.
Thank you, Julien. That was a very nice talk, for which I thank you extremely much. And in fact, I have to tell a little secret. It is today my birthday.
Oh,
so
happy birthday.
It could not have been a better birthday present. It was excellent. Thank you very much. So now we come to the session of the questions. So I have foreseen 15 minutes for the question. How we will organize it is, in the following. Could you, if you have a question, raise your hand. There's one of the buttons on the bottom or somewhere on the screen, which is called reactions. And in that, if you click on the button, there is a field raise hand. So if you raise your hand, then I see it and I can give you the word and have the question raised to Julien. 1 minute, I will now check for the participants. I have to see myself because I have to learn a little bit. I've seen 2 hands which were raised already.
At least 3. Yeah.
Yes, I have them here. Yes. So the first one was by Alexander Séverin. Alexander, you could ask it to Julien now if you wish.
Yeah. Thank you, Julien, for a beautiful talk and a happy birthday to Jeff. This is not a critical question, but just wondering. I'm a physicist. We consider fusion as some local violation of Lorentz invariance, because when I started studying physics in '81, I was told in my lectures that it's 50 years away. When I became professor at the beginning of the '90s, I was told it's 50 years away. And now on your last slide, you go from 50 to perhaps 100 years. So how is, if you think about fusion as really as a realistic source of power for humanity, what is now a bit the consensus amongst the specialists when we will have the first commercial fusion reactor?
That's a debate among specialists themselves, I would say. There is the optimistic way, I would say, and there is probably the more realistic one. So if we are very, very optimistic, so let's suppose ITER will be a success, but however, the ITER will give interesting results not before 2035. So the DT experiment in ITER are not planned before 2035. That means even if it's a super duper success, that means, let's say in 2036, we know it will work. So we know if it not works. So from that, we need to take a decision. So of course we can anticipate a little, but we will not have the definitive result from ITER before that date. That means, of course, you will not have political decision probably before that date too. So you will not be able to build the demo reactor before 2035, obviously. You need few years to build a reactor, or let's say we are already, everything is, we are just in the starting block, and as soon as we got a green result from ITER, we built a fusion demonstrator in 5 years. Very, very optimistic things. That means by 2040, we could start a fusion reactor. This is the most optimistic things. But after, the thing is probably getting worse, because even if you achieved a fusion reactor in 2040, it's only one, and it's a demonstrator. So let's say here in this picture from colleague Greg de Termeman, it's not 2040, but it's 20 years after. So your first demonstrator is here. Let's say after your demonstrator, you want to build 10 power plants. You need time also to find investment and to build it. You see, if you make the calculation, that you will only achieve the 1% of the current world total installed power only, let's say, before the end of the century. Before the end of the century, the optimistic path, maybe you can be more optimistic in the trend. I mean, you can have maybe a derivative that is more optimistic, but anyway, you will not be able to have few percent of the world total installed power before the end of the century. Except, of course, if everything crashed down, and in this case, the thing could be different. But I mean, this figure is already rely on a certain assumption, could be indeed, could be discussed, and it is discussed between the specialists. Could be more before, but no, that will not 2050.
Thank you. So that means I will not be there, but if my children are a bit lucky, they might still see it. Thank you.
Thank you, Alexander. The next question is by Frank Ferrari. Frank, please.
Yes, so thank you very much for this very, very nice presentation. So unfortunately, I have too many questions, so I have to pick up some. And since Alex asked, I think, the question that everybody is willing to, to understand, I will keep going on this, or maybe I have some version of it. So first of all, I would like you to comment, if possible, on the recent very exciting announcements by the Spark spin-off of MIT. You know, they announced that they've made a breakthrough in the superconducting magnets, and that is maybe is going to change completely the picture for how long do we need to get to fusion. So what do you think about this? And related, of course, to that, how much the delays you're talking about depend on the public funding actually that we have? In my opinion, or it's my feeling, it looks like this ITER project is extremely slow You know, it's been an amazing collaboration between many, many countries around the world. So from that point of view, it's a great thing, but it doesn't look to be very efficient to me, you know, to have hundreds of different parts built in dozens of places around the world and shipped, etc. So there's a lot of management involved and probably slows down a lot the process. So also, do you have comments on that? You know, if the private industry takes this seriously, cannot we, you know, multiply by a very high factor the speed of progress?
Yeah, so the answer is maybe, but the second answer is pay attention to the announcement. Okay, so the result from MIT is a great result. What they have proved is they have proved that they know how to build and operate a coil, a magnetic coil, which is made of different superconductor than the one that we are currently using. This is what we call high temperature superconductor. And they have demonstrated they can build a real coil that produces 20 Tesla at the conductor itself. So it's I mean it's a breakthrough in the way that it has never been achieved to build such a coil like that. It could have impact on fusion because, as I say, in order to reach initial and sufficient level of net power, you need this combination of three factors: density, temperature, and confinement time. And if you increase the magnetic field, you will increase the confinement time. You will increase it by a lot. And that means instead of having a big machine for the same reason to increase the confinement time, you can keep a smaller machine, which is probably cheaper to build, with a higher magnetic field. That is, I mean, they are using exactly the same equation that has been used in order to calculate the dimension of ITER. Instead of increasing the size of the machine and to reach the design goal and the design of ITER, they instead play on the magnitude of the magnetic field, and this produces a smaller reactor, which could be cheaper. But there is a con with that, because if you produce the same amount of power in a smaller volume, if you do the calculation, you will have a higher flux density that goes out of your plasma, and you need to handle that properly. And so far, I mean, calculation can be done, and some are optimistic, some are pessimistic. It has to be demonstrated that you can handle such a power density, which is a factor of a few with respect to what we already know how to do. So that's the first point. So maybe, yes, but there is a lot of things to demonstrate before. Maybe it will accelerate that curve, and probably, and I really wish it. But the takeaway message with that curve is that even if today there is a magic solution that comes here, you will need some time in order to build the infrastructure, the electric lines in many countries in order to achieve a certain amount of power. And until you reach a certain portion of the total installed power, you will have some concurrent. You will have some people looking to you, and then maybe playing with the price of things, I mean, markets, etc. So things can also be more complicated than that. And you are right, for the way ITER is working, we can sometimes consider that ITER is slow, but we have to remind that ITER start as a political project. So indeed, all the components, I didn't speak about that, but all the components of ITER are built in the different country of the ITER partner and are all gathered to Cadarache. And sometimes the same component is built in different countries, which require indeed a lot of management. So of course, a private company will be much more efficient in building a reactor. Yes, I believe so.
Okay, thank you very much. I mean, if there is time, I can ask more questions, but later at the end. Thank you very much.
So Frank, I have a solution for you. If you could, put in the chat your other questions and put your email address, I will copy this and send it to Julien, and then you will provide you an answer whenever there is time, or you could perhaps even have interpersonal contact by email or telephone, whatever. But please put your questions in the chat. I will copy them and put your email address or a telephone contact so that they can be replied. Is that okay? If we have more time, we can still do one today, but I would like to give first also the word to Professor Tikhonchuk, who has also a question. Vladimir, please.
Thank you, Julien, for a very interesting talk. But you see, the questions are going in between two limits which you are presented, inertial fusion and magnetic fusion, and these two ultimate limits. And people are interested in, could we find a way, something in between, which would be more efficient and more fast? And in my question, it concerns the hybrid approach, when fission and fusion can be joined in such a way that the negative features of both approaches could be a little bit mitigated and the benefits could be mutualized. What do you think about that?
Yeah, I know this approach exists. So the idea for the other is to put to create sort of a fusion plasma that create neutrons, high energy neutrons, and to put outside of your fusion reactor some fission materials. And when they will receive neutron, will produce also energy by fission. So you
can incinerate this highly reactive material which produced in fission reactions.
I mean, yeah, I'm not at all a specialist of this technology. The only thing I see from the political difficulties is indeed to combine both currently, because currently, as soon as you are speaking about fission technology, and it's a bit complicated to have an unpassionated debate. So that would be for me the main problematic if one would like to push this solution. But however, I know that this solution is strongly pushed, particularly in Russia. So there is some experiment that, at least there is some wish to make this kind of experiment in Russia.
Calculations show that one fusion reactor could provide the fuel for 10 fission reactors and incinerate so it might be a good solution, but for some reasons, both communities are very reluctant to collaborate.
Yeah, you're right.
Okay. An answer to your question, Vladimir?
Yes, thank you.
Okay, thank you. Then we have another question by Nick. Nick, perhaps the family name could be mentioned?
Nick Schrijvers, dag chef.
Nick, okay, very good. Nick.
Hi. Yes, thank you very much. Very interesting lecture presentation. I was wondering, you mentioned in the slide where you talked about the sustainable sources like solar cells and wind power, that they have a bit of a problem with mineral resources. But then in the course of the fusion, you need lithium to produce tritium, if I got that right.
Yes.
So is there any risk that we are running out of lithium when using that for fusion?
If everybody goes into electrification and still using a lithium battery, probably at some point that could be the risk as well. But the resources in terms of lithium are still much higher, and there is a lot of progress recently in the way that lithium is extracted. With less polluting techniques, much less efficient techniques as well are coming in. So probably you will have some difficulty to find rare materials, rare earths, before you will have trouble to get some lithium.
Okay, thank you.
So thank you all. I don't see further questions. I repeat again, if you have a question still you want to ask, perhaps we can still take one. Otherwise, put them in the chat or send them to my email and that of Julien. I will put it to everybody then, if you wish, so that you can send us these things and we will reply you as soon as we can. Otherwise, there's still, of course, time to answer any other questions on the direct subjects, because this was a general talk. There will be specific talks on the different subjects, as Julien has very clearly indicated. You can also raise your questions there with the specialists on their specific topics, and they can go in more detail in your question as it was now possible, I think. So don't hesitate to contact us. You can send the emails to the Belgian Physical Society, which is BEL, B-E-L, PHYS, P-H-Y-S, and then again S-O-C @gmail.com. BEL, PHYS, SOC @gmail.com is the email. I will put it in the announcements also. It is also in the announcement, in the bottom of the announcement, you find there the email address. You can send it also there. We will pick it up and get back to you and reply. So I hope you all enjoyed it. I hope that you learned several points here. That is indeed the intention, to make you aware, to make fusion accessible, to see how it fits in the full picture, which I think was very well done today. And as I said, don't hesitate to spread the information on these webinars to other people which would be interested, with colleagues, friends, whoever you know. It is indeed the intention to make this as public as possible and to have a discussion with the members of the public. So I thank you all very much. And I would like to close the webinar and see you all back on Tuesday, not on Wednesday. This is exceptional because Alberto could not make it on Wednesday. It will be Tuesday, the 5th of October at 4 o'clock. The other talks are all on Wednesday. Some are a bit shifted in time, but they're on Wednesday. This one, the next one, is exceptionally on Tuesday. Thank you very much and have a good evening. Bye-bye.